We're continuing in our building of a residual graph from a graph. So what I think I'll do in this case, we've got these two rules here that we want to apply to a graph. And so I want to think about what would happen if I take a, my chair is real squeaky, sorry about that. What happens if I take an edge from the original graph that goes from U to V, right? And it has a, let's say it has a capacity of 17 and a flow of 6. Okay, what do these two rules tell me to do? This says, let's see, for each edge, E, U to V, and FE, which is 6 in my case, we create a backwards edge. So on, let me draw that over here. Maybe we'll draw that in red. So U, V, so this is graph G, and this is going to be the residual graph. So what we're being told up here is we're taking a backwards edge from V to U, right? And it's going to have the value 6, and so that's going to be called the residual capacity. Okay, so that's residual capacity. Okay, now I'm not finished yet. For each edge E, right, and this is my E, and my FE is less than my CE for this edge, I create a forward edge with CE minus FE is going to be the value there. So that's going to be 17 minus 6. 17 minus 6 is 11, and so that's going to be the residual capacity at the top. So you see what's happening here? These flows are telling me how much capacity is left going in each direction rather than just in one direction. In this case, you kind of have to figure out what's left over, but here you're being told. And so you can actually take the path from V to U, which means you're just giving up some of the capacity that or some of the flow that you've already accumulated. So it is possible to go backwards on these graphs. And so that's why this residual graph is really handy, because it explicitly tells you that you can do that. Okay, so let's go ahead and maybe I'm going to pause this for a second, and I'm going to draw a graph with a flow on it, and then we'll just draw the residual graph from that. Okay, so the graphs have appeared now. And so on the left here, I've drawn a graph with a flow on it. And I want to go through, and each edge on G, I want to create GF. Okay, and so here, the very first edge here is 20, 20. So that means that I just go backwards from here to here is in 20, right? From S to 2, I've just got an edge with 10. There's no flow on that, so that just stays as 10. Okay, similarly from 2 to T, I've got 20, 20, and so I'm just going backwards then. I draw my backwards edge, which is 20. This one has a forward edge of 10, right, because it doesn't have a flow. So really the only interesting one might be this one, right? So what does this say? I can go backwards 20, okay, backwards 20, and then forwards, what's left over from, I started with using 20 out of 30, right? So I've just got 10 units left that I can go down with. Good. And so this is a finished product then. The graph on the right is the residual graph. Good. All right, let me pause again, and I will set up a new example. Okay, so my new example is ready to go. I've got a graph here from S to T. And the way we're going to be, we'll be describing what's called the Ford-Fulkerson algorithm. And the way it works is initially you just pick a path. Pick a path, any path from S to T. What's a nice path? Well, might go ahead and just take this upward path from S1 to 1 to 3, and then 3 to T. Okay. Oh, you know what? Let's take a more complicated path just to be fun. How about if I take 1 to 4, just to be complicated? 1, 4, 3. 1, 4, 3, T. Okay, so that's my path, and I will denote it with its edges like that. S1, 4, 3, T. Good. Remember how to compute the bottleneck? The bottleneck is the minimum value along the edge here, and so that is a 6. And so B is going to be 6 in that case. Okay, so that gives me, I can go ahead and put my 6 here, 6, 6, and let me erase that, and we'll say 6, 10. Good. All right. Now, before we go any further, can we write down the residual graph from that? Not what that's doing there, and I don't know what that's doing there either. Okay, so here we had a forward path of 6, so we go backward 6. This one stayed forward as 0, so that's going to stay 10. I guess that one's going to stay 9. That one's going to stay 10. Now this one actually goes 2 ways, right? We have forward 6, so we can go backward 6, and then we have a full capacity of 10, so that means there's 4 left over. This 4 wasn't used yet. This 2 wasn't used yet. And then this 6 was used. It was all used up, right? So therefore this path ends up going backwards with a value of 6. And then this one in the diagonal, right, goes backwards 6, forwards 2. Good, so that's my residual graph. And again, the residual graph is here so that we can figure out, oops, something's missing, isn't it? I forgot my forward. I still have forward path here of 4. Good, now I finish. Good. So this is my full residual graph. And now I want to figure out a new path from S to T. So which should the next path be? Well, you can do quite a few of them. Shall we just go down and around here? So we'll just go this way. So that was here on this graph. And so that would just be S2 for T. Okay, and then that bottleneck value is 9. Okay, and so then that doesn't touch any of the edges we were just on. So this becomes 9, this becomes 9, this becomes 9, and then we can just change these 3 edges down here. That'll make that a little bit easier. So I'm going back 9, forward 1. This one just goes backwards 9, and this one goes backwards 9 and forwards 1. Okay. Do we see anything else that we might be able to use to get from S to T? Boy, do you see this one? This one's kind of staring right at us. We have a 4 going forwards, 4 going forwards, 4 coming over this way. Let's go ahead and take that one next. So that would be S13T. And what's the value of the bottleneck there? That's 4, right? And so what's our flow so far? 4 plus 9 plus 6 is 19. Okay, let's keep that in mind. So now I can come back up here and change these values. Okay, so now I have 4 in my flow. I've maxed this guy out. That's now 10. This guy is now 10. Good. And so therefore, on my residual graph, I just have a backwards 10 here, a backwards 4 here, just a backwards 10 here. Okay. Any other way of getting from S to T? Well, the only way I could do it, the only way I can get out of S, right, from the residual graph is to go from S to 2, right? But if I do that, what happens? Can I go anywhere? I can't go to 4. I can't go to 1. I can't go. I could go back to S, but that would just create a loop. So then, therefore, I am done. We have a flow of 9. What was it? 19? No. 6 and 4 is 10, and 9 is 19. Yes, flow of 19. Good. And now this is the residual graph, right? And so this was our finished flow. Right, so this is our flow up here. Very good. All right, so that is the Ford-Fulkerson algorithm. So again, the steps are: you find a path, you create the residual graph, find a path, look at the residual graph, find a path, look at the residual graph, and the residual graph will tell you when you are done. Okay, so we're going to continue this example to take a look at a cut. See how the cut is used for the graph. Okay, we'll be right back.